Hi guys, my group is doing relative velocity, which is part of relative motion. So let's look at a quick example here to try and explain to you what relative velocity is. So we have Mario right here, right? He is walking 2 meters a second on a treadmill going 2 meters a second, okay? So we want to find out what's Mario's velocity compared to us. Now we're the velocity frame, we're going at 0 meters a second, so everything's going to be relative to us. So let's look at that on paper and try and make more sense of it, all right? So this is what we got. So the velocity of the vector of Mario to the treadmill is equal to 2 meters a second, because we know Mario is moving 2 meters a second on the treadmill. Now the velocity of the treadmill to us is 2 meters a second, because we're 0 meters a second, and then the treadmill is moving 2 meters a second. So now if we want to find the velocity of Mario with respect to us, it's as easy as vector addition. So what you do is the velocity of Mario with respect to us is equal to 2 meters a second, which is the one up here, plus 2 meters a second once again, which is the velocity right here. So you add these two vectors together, and then that'll give us the velocity of the vector of Mario relative to us. And then that would be 4 meters a second. So now let's look at something just a little bit more complicated, not really. So say instead of Mario moving 2 meters positive a second with a treadmill, he is moving negative 2 meters a second relative to the treadmill. So we're just going to change this value to negative 2 meters a second. So now all this does is it changes the value here, which we took from here earlier, to negative 2 meters a second. So whenever you add these together, you're going to get 0 meters a second. So the velocity of Mario compared to us is going to be 0 meters a second. So even though both the treadmill and Mario are moving, it's going to look like he's not going anywhere. So here's an example of
that. Dude, that's pretty good.
All right, now here's an example of the car going a speed, but Eli drops the rock without pushing it, so the rock's velocity is 0. All right, now here's an example of the car going slower than Eli throwing the rock. All right, so we're going to add another dimension to relative motion. So before we were just on an x plane, which was flat, because everything was going in the same direction as each other, or the exact opposite, no in-betweens. But now whenever we add directions, such as north and west, there is in-betweens, and then this gives us an x and y coordinate plane. So let's look at Mario and the treadmill. Both of them have the same velocities, except now there's different directions. So the treadmill is going to be moving to the west at 2 meters a second relative to the Earth. Now pretend this table is the Earth. The Earth is our velocity frame, so its velocity is 0 meters a second, right? So now we're going to be also looking at Mario, and instead of Mario going the same direction as the treadmill as in the last experiments, he's going to be going north. So he's going to be moving this way while the treadmill is moving this way, right? So now what we want to do is we want to find the velocity of Mario with respect to the Earth. So this is how we're going to do that, right? So the first bit of data we got is the velocity of the vector of Mario to the treadmill, which is this, is 2 meters a second north, right? And then the velocity of the treadmill with respect to the Earth, I did a U there. The U is supposed to stand for Earth. Let's change that real quick. So that's an E. So the treadmill with respect to Earth is 2 meters a second west. So we can't just simply add them now because there's an extra dimension that we need to figure out. So what you do now is you do triangles. So I'll get back to you once I fill out the triangle. All right, so now we have our triangle. So the way I set up this triangle is going off north, east, southwest. I just did the vectors in the direction they're going. So we have this vector, which is the treadmill with respect to Earth, which is going 2 meters a second west. So it's going west right here, as you can see. And then we also have the velocity of Mario with respect to the treadmill is 2 meters a second north. So we have it going this way, right? So now, if we want to find the velocity of Mario with respect to the Earth, we need to find this on the triangle. In this instance, it's the hypotenuse. So in order to figure this out, what we need to use is the Pythagorean theorem. So everyone should know the Pythagorean theorem, and that's pretty much a squared plus b squared equals c squared. So what this is it's the two side lengths, both squared, both added to each other, is equal to the hypotenuse squared. So this is our hypotenuse squared. So pretty much what we need to do in order to solve for this is we need to plug in the values for this. So 2 meters a second is one of the side lengths. So 2 squared plus another 2 meters a second, 2 squared is equal to the velocity of Mario with respect to the Earth, and then squared. And then by solving this, we will be able to get the velocity of Mario with respect to the Earth. So 2 squared is 4 plus another 4 is equal to the velocity of Mario with respect to the Earth squared. So now we add these two together, which would be 8. And then we also need to get the square root of these guys. So if we do square root here, basic algebra here. So if we get the square root of 8, boom, will be equal to the velocity of Mario with respect to the Earth. So you simply just solve that out, round it to the significant digits, and then basically by doing that, you'll get the velocity of Mario with respect to the Earth, and that's pretty much relative velocity in motion with 2 dimensions, x and y. Thank you for watching our video, and have a great day.